Previously, we talked about work, and we know that work is when we apply some kind of force and it causes something to move. And it relates to that force and the distance in a way that it's a measure of energy and it's the changing of the energy. Well, what is the energy? And a lot of people define energy as the ability to do work. And you have this what's called a circular argument of things, but it really doesn't help explain it. So today we're going to start looking at what is energy. And the first one we're going to talk about is something called potential energy. Now, potential energy can come in many different forms. You might have a chemical reaction that's going to produce energy. And so, when you have your two reactants or three reactants that you're ready to put together in a chemical reaction, then you would have what we call chemical potential energy. Or maybe we stretch an elastic or a spring and we're going to shoot a bow and arrow. And that would be an elastic potential energy, or there's a nuclear reaction happening, or a nuclear power plant, or on the sun where we have energy being generated for our solar system, then that is a radiation or a nuclear energy going on. So there's lots of different types of potential energy. But the one we're going to look at is mechanical potential energy. And really what it's due to is it's due to an object moving, some mechanics happening, and this is related to gravity. Here I have a white golf ball. Here I have a ping pong ball. And they're roughly the same size, but hopefully you know that they're not the same weight. And what I need to do is I have a switch on the floor that I want to drop these, and I want to see if this can flip a switch. And by flipping that switch, they're going to do some work for me. Do you think they would do the exact same amount of work? I guess the real question is, if they're doing work, they're applying a force. Which one would apply a greater force? Or would they be the same? What did you figure out? Which of these does more work? I'm hoping you realize that this ball would put greater force when it lands. Why? It has a greater mass. What else could I do to increase the force that this creates? Well, let's consider it. What if I drop it from this height, or if I drop it from this height? Would it hit with the same force? What other factors do you think would influence the force it creates? So we've seen that we want to have some kind of energy. I'm going to use the symbol E for energy. And we talked about its mass. And as you increase the mass, I hope that you'll recognize that you would also increase the energy, the potential energy that it has. Now, I will mention that potential energy, some books, some teachers, some websites will do this. They'll go E with a little p for potential. Other teachers will just write it as PE for potential energy. I tend to do this one more often, but others will do this one more often. Okay. But as you increase the mass, you're going to increase the amount of energy that something has. In other words, I took a ball, let's say that weighs, I don't know, 5 grams, and I took another ball, let's say the same size, that weighs 30 grams. And if I drop them from the same height, this one has more energy in it. This one has less potential energy. Okay? So then the question was, well, what else affects the amount of energy something has. And then I asked the question, okay, what about the height that I drop it from? So if here's my floor and I drop a ball from this height or I drop a ball from this height, which one has more energy? Okay, we'll call that H for height. Make a double arrow, okay? So, and I hope that you would recognize that this one has more energy. It has more potential to do work. More potential to do work. Okay? Like I said earlier, if I have a switch on the floor that I want to I want to trip, and I've got this switch that needs to get sort of knocked down, which one is more likely to do it? And I think this one over here would give us a little bit more energy. What else would affect these things? Okay. Well, what's making it move? Well, gravity is. And, you know, would it be the same if I dropped it on Earth or the moon? So, gravity of Earth versus gravity of the moon or Jupiter or the sun. Okay. And this is the larger one. Okay. So there is a direct, they're called directly proportionate. And what directly means is that if I if m doubles, then e doubles. And if m triples, then the energy would triple. Okay, so this is proportionate. For those that don't know, sometimes you get things that as you if other options, I can call it, that they don't happen with what we're doing, but other options, if x doubles, y increases 4 times. Okay, that is not what we have going on in this situation, right? So that's not what happens here. Okay, we have this directly proportionate. And as one goes up, the other goes up. And our physicists knew this for thousands of years. So what they've done is they've come up with this formula for potential energy. And this is what we need to know, that our potential energy is the mass times the gravitational force times the change in height or the height that the object is at. Okay, so very, very simply, so, here's a floor and, maybe here's my desk. And if I was to lift a textbook up to the desk, and let's say, so here it is, and let's say that this is 1 meter high. Let's say it had a 1 kilogram mass. What is the potential energy? So I know that the potential energy is the mass times the gravity times the height. So the mass of 1 kilogram times gravity, 9.81 meters per second squared, times the height of 1 meter. And that would give us an answer of 9.81. Now we need to get the units figured out here. So let's see, I've got a kilogram. I've got meters per second squared times meters. And what that's going to give me, 9.81 kilogram meter squared per second squared. And we've seen that unit before. We've seen this before. Guess what? That's a joule. So we have approximately 10 joules of energy. Okay. And if that book fell off, then it's going to fall down back to the floor. Okay. And when it's down here, it has 0 joules of potential energy because it has a height of 0. Here is a couple of examples. I have an apple hanging from a tree, and it has a mass of 85 grams. And I'm going to right away convert that into kilograms. That's 0.085 kilograms. And it's hanging at a height of 4.29 meters. And let's not forget that gravity here on Earth, 9.81 meters per second squared. So how much potential energy does it have? So our potential energy is simply the mass times gravity times the height. So it's 0.085 kilograms times 9.81 meters per second squared times the height of 4.29 meters. Remember that this is going to give us a kilogram meters squared per second squared, which we know is a joule. Okay, so if I multiply that together, I'm going to get an answer of 3.577 kilograms meters squared per second squared. Or if I round that off, let's call it 3.6 joules of potential energy. Meaning that if that apple were to fall, it has the potential to do 3.6 joules of work. Okay, here's the second question. We have a water bottle, mass of 756 grams. Once again, right away, I'm going to put that into kilograms. And it's on the floor. So we got a height here initially of 0 meters. Then we're going to move it up a little higher, and we're going to put it up to 75 centimeters. Okay, once again, I'm going to immediately put that into meters. Okay, so part 1. What is the potential energy while it's in your book bag? Well, we don't really need to, but I'm going to do it anyway. I'm going to say, well, potential energy is the mass times gravity times the height. But in this particular example, I know that height is 0. So this has 0 joules of energy. Okay, it's in a very stable spot on the floor. The second question, the potential energy while it's on your desk is going to be the mass, which is 0.756 kilograms multiplied by 9.81 meters per second squared, multiplied by the height, and the height here was 75, 0.75 meters high. And so what we're going to see this time is we're going to see a potential energy of 5.6 joules of energy while it sits on your desk. Okay, and that's our potential energy. It has that much potential to do work. Part 3, bit of a theory question. What work was done? Well, we know that work is the force times the distance. And we know that the distance it was moved was 75 centimeters or 0.75 meters. But we don't know the force. So we can't solve it, or at least that's what we think. But really, what it comes down to is this right here. Okay. This tells us that it has 5.6 joules of potential energy. And so our change in energy, it went from having 0 down here on the floor to 5.6 up here. So we had a change in energy of 5.6 joules. That means that there was 5.6 joules of work done on the water bottle. I have a car. I'll draw this here. Oh, it's a steep hill. All right, I've got a car. My car's black. I'll draw a black car here. I got a car on the top of a hill, and I want to know how high is the hill. And what I know is that we have some potential energy that we calculated was 238 kilojoules. First thing I'm going to do is I'm going to convert that. I want to get this into the fundamental units that we use. Well, not necessarily the fundamental units, but the main units. So that's 238,000 joules. If you want to put in fundamental units, we could go 238,000 kilogram meter square per second square. Those are our fundamental units. What else do we know? We know that the car has a mass of 957 kilograms, and that's good. See, this is in kilograms and that's in kilograms. That's helpful. And of course, we also know that gravity is 9.81 meters per second squared, which is really helpful. We get everything down to kilograms, meters, and seconds. Now we can solve that. So we know that our potential energy was the mass times the gravity times the height. So if we want to know the height, we do a little bit of algebra here, and I say, well, the height is the potential energy divided by the mass and gravity. So we've got 238,000. I'm going to get rid of the joules. I'm going to go to my fundamental units because it helps me figure out if I've got the right answer and units and all that stuff. Divided by the mass. The mass was 957 kilograms. And then 9.81 meters per second square. One of the most common mistakes I see students making is the order of operations. We've got a divide sign, and then we're going to multiply on the denominator here. So I'm going to put this in brackets just to remind you that we need to deal with the bottom here before we divide. Okay. I'm going to look at my units. I got kilograms on top. I got kilograms on the bottom. Well, I've got 2 meters on top. I got 1 meter on the bottom. That'll cancel out. I got seconds and seconds down below. I'm going to be left with the units of meters. Well, that's good because I want my height to be in meters. And when I hit the numbers on the calculator, I'm left with 25.351 meters high. That's the height of my hill. So that's pretty good. That's not too hard. The second question here says, okay, now the car, we're going to take our car, we're going to drive the car down the hill, and now it's gone down the hill 15 meters. How much potential energy does it have now? So there's 2 ways you could figure this out. You could figure out what is my potential energy here, or you could figure out how much energy was lost. And I'm going to do it with the energy lost, but you could just figure out the new height. The new height, it's gone down 15. So the new height, height number 2 would be roughly, what's that, about 10.351, I think would be their new height. So we could just go, our potential energy is mgh and use that height. But I'm going to do it a different way. What I'm going to do is I'm going to figure out how much energy was lost. So I know that I had how much energy at the top here. I had 238,000 joules of energy, and we are going to lose some energy. So we got a loss of energy here, and I could just find out how much I lost, subtract them, and I'd know how much energy I have now. So that's easy enough. I'm just going to say that the potential energy, in this case, it's the potential energy that was lost, is the mass times the force of gravity times, I'm going to use delta H just to say that it's a change in height. Okay, so what was my mass here? I had 957 kilograms times gravity, 9.81 meters per second squared, times the change in height. The change in height was 15 meters. And when I put these numbers into my calculator, I'm going to see that I have roughly 140,820, I'll say 23 joules of energy lost. Okay, where did it go? That's tomorrow's lesson. So if I started at 238,000 joules and I lost 140,823 joules, I now have my new potential energy. And what I have here is I have 97,177 joules of potential energy after it's gone partway down the hill. That should be enough to get us going with understanding potential energy.